Okay, good morning. Today is March 23rd. Today we're introducing chapter 25. We still have about less than 2 weeks before our spring break. Or is it more than 2 weeks? I really lost track of. I think it's more than 2 weeks now. I have no idea. I'm lost track of numbers. Anyway, do you know, Marcela?
I think it's the first or second week of April.
You don't know much. Okay, so we should be able to get chapter 25 and 26. You will see that chapter 25, I will not really do a lot of problems with this chapter, maybe 2, potentially 3 problems, okay? Because I'm going to reserve a lot of problems for chapter 26, where we're going to actually tackle more circuits, where we're going to actually have stuff in it, namely the resistor and the capacitor and all of the other instruments put together in one circuit, and you would be dealing with the power source and how things are. By the way, if you hear some noise, please, I'm sorry, I apologize for that. There's a guy who's supposed to be fixing the AC today. Okay, anyway, so basically, chapter 26 will have a lot of components in it. We already discovered quite a few of these components. We discovered the battery, we discovered the switch, we discovered the most important of those 3 is actually the capacitor. And we saw how the capacitor basically stores charge or stores energy and basically can be used in parallel or series. Today we're going to discover another instrument called the resistor. So once we have the resistor and also the capacitor, we can start putting things together in what is known as an RC circuit. Chapters 21 through 26 are part of exam 1, which is going to be immediately after spring break. So it's very important that we focus on these chapters before the spring break. I'm not sure, honestly, if we get to magnetism and chapter 27 before spring break or not, but if we do, it's not going to be included in this exam or midterm. Okay, so I'm going to share the screen with you guys. Okay. And the chapter 25 again deals with the resistors. So let's try to understand what's going on. There are basically, in material science, 4 kinds of materials. There are conductors, which we're going to be focused on today. There are actually insulators, which are the opposite of what conductors do, insulators. And there are 2 kinds of materials that we're probably going to briefly talk about in this class. One of them actually more so than the other, semiconductors. And also superconductors. Superconductors, the theory behind them is kind of a little bit not easy to understand because it involves the pairing of electrons and how they attract basically the ions toward them and move freely with no resistance. Whereas in these 3 materials, you always have what, at least the theory for them and what's going on is you have each atom provides 1 or more electrons for conduction. So in the case of conductors, in this case, you have a band of them that are available in the conduction zone. So when there is an electron in this, when there is an electric field in this case, they will start moving at will, okay? Because they're available, and each atom provides 1, potentially 2 electrons. This is basically how the theory goes, because you cannot really do more than that. And they start moving, and those are usually on one side of the periodic table. Okay, so those are the materials that are good conductors in general, and the closer they are on this side of the periodic table, basically in the S state, the closer, the better the conductivity is, okay? With the exception of hydrogen. Hydrogen is actually none of the above. So lithium and all of the other elements in periodic table on that side are of this type. Magnesium, sodium, all of these types are supposed to be good conductors, all the way to iron and everything else. So those are the focus in here, okay? So they have available electrons that don't belong to a specific atom per se, but they are moving. At every given point, an atom actually is neutral still, because if one electron somehow is pushed by the electric field from it, another one, because they don't belong to the next door neighbor either, just as much as it doesn't belong to it, it belongs to the community of the atoms, so it's going to grab another one to sub for it. So it stays neutral. So it stays the charge is zero charge at all times, no matter how fast these charges are moving. They're always being replenished because there is plenty of them available in the so-called conduction band in this case. Okay, this is the valence of the. Whereas, for example, in the insulators, you don't have hardly any of them. Obviously, with temperature, some of them will jump and become available. So even an insulator sometimes can conduct if the voltage is high enough. So that is actually the dielectric breakdown. So this is basically what's going on with the insulators. So the insulators don't have this scenario. So if you apply an electric field, the atoms are strongly holding the electrons with them. So if in case one of them tries to move, it can't move easily because of this fact that the bonding is strong in this case with the atoms. So you can apply a very, very large electric field, in which case you can yank this one out of there and you have conductivity, and that is the lightning. Okay, in the case of semiconductors, the gap between these two zones are actually small enough that sometimes with a little bit of help, they become good conductors. Otherwise, they're actually insulators in nature. So like silicon and germanium, those are semiconductors. So what you do in that case, you do something called doping. So what you do in this case, you take, so this is the gap between the two bands of conduction and basically where this is full, okay, so this is not available. So what you do in this case, you take a doping and you make the doping in such a way that it's going to give away electrons. So this is actually going to be a donor. So and now electrons are available in the conduction zone and they can move in this case. So you have a net negative charges in this case because it's a negative charges. You call this type of doping an N type, okay? Because you brought an impurity in this case. Impurity is just large enough so that you have a lot of electrons available, and now this behaves as a good normal conductor, just like a copper a copper wire. Or you can do another one. So this is actually a donor. Or you can do actually an acceptor. So actually those are the same two bands. So this is full. This zone is supposed to have immediately a charges to move in it, negative charges to move in it. So what you do bring in here, you bring an acceptor of this zone closer with the gap very close from the band where that is full, that does not normally conduct. So in this case, what it does in this case, it takes one of these electrons and moves it in here and moves the electrons to this zone, not all the way to the gap in here. So they don't move the electrons because they are anchored with the impurity. So this impurity in this case will leave behind a zone that is lacking electrons. So this is called actually a hole, leaves a hole behind. And when you apply an electric field, the holes will move in the opposite direction. Okay, I mean, they will move in the electric field direction actually. So in this case, if you apply an electric field this way, the electrons will move in the other direction, resulting in a current flowing in this direction still. So in this case in here, what's going on is the hole, which is a positive charges, will move this way. The impurity cannot move because it's too heavy. So in this case, the conduction is done by holes or positive charges. That's why this one is called P-type doping. So again, we're getting a little bit ahead of how it's going on in terms of the materials for semiconductors. But before we understand that, we really have to go back into conductors because they are a little easier to understand what's going on in them. So imagine with me the following picture. So what I have in here, I have a piece of wire of a good conductor. Think of it as copper or whatever material that you choose to think of. Okay, so this is a cross section A of it. This is the area basically, and I'm taking a finite length L. Obviously, if I apply an electric field in here, charges start to move. But before they do that, I have a bunch of them. How many do I have? I have a huge number of the order of 10 to the power 18 or so. Okay. Actually, of the order of Avogadro's number per mole. Okay. If this is a material that provides for me a lot of charges, then I'm going to assume that it has actually more. So what I want to characterize this material, because the conductor is the number of carriers, N So don't confuse the N symbol in there. N is for negative only. So this is the doping for the semiconductors, okay? I'm talking about the number of charge carriers. So what I'm saying in here, I didn't know anything about electrons, and of course we don't necessarily make any assumption about the fact that they are electrons. Let's call them charge carriers Q, okay? Obviously Q in magnitude is equal to E, 1.6 times 10 to the negative 19 coulomb, at least in practical. But what I'm saying in here, it's a number of charge carriers per unit volume. If you are a good conductor, you provide a lot of this. If you are a bad conductor of electricity, you provide very little, if any at all, okay? So that is basically in a nutshell. So every material, copper, for example, depending on the intensity, the density of copper, so this is actually related to the density of the material, for sure. And it's also depending on the valence of that material. How many electrons can this material make available for me to move? So some of them will give you 1, some of those will give you 2, the others there is other combinations. And if it is an alloy, not necessarily a metal, then in this case it can work out the number differently, depending on its density. In other words, how many atoms are in there in a unit volume, and each one of them how much it can afford to give to the whole community. Based on that, we come up with a number that is characteristic of the material. So this number is characteristic of the material. So how do I know this number? You can solve the tables, okay? Look at the tables. This is a fixed number. You don't really mess around too much with it. So this is something that has to do with the density, which you cannot control, and also has to do with the chemistry, if you wish, or the how the electrons are distributed, you know, the SPDF. Any one of you took chemistry already and know about the SPDF and things like that? No?
Yeah, I'm in chem.
Okay, very good. If you didn't take that class, wait until you see that stuff in physics for D, okay? That is going to come with vengeance if you're going to take that class, okay? You should have quantum mechanics in that class and hopefully understand atomic physics a lot better. Anyway, so that number is coming from there. Obviously, that is one parameter in the whole thing. So in the normal circumstances, what's going on? With temperature, and again, if you're sitting in 4C, you probably have an idea of what's going on. And actually, that's actually the topic of chapter 18 in that class. So what's going on in this case, we're going to treat now this number of electrons, which is a large number, by the way. This is per unit volume. So if I take a big volume of this, so I have a bunch of charges going a lot, okay? So it's a huge number, okay? So of the order of Avogadro's number, if you really want to have the actual number. I'm not talking about this is the density. So if I want to find the actual number for this piece of wire, I have to take the volume, which is A times L, and then multiply by this density, and then I will have a huge number in there, okay? Here is what's going on in a normal copper wire because of heat. So what you get in here is that this electron is moving one way until it collides with an ion, which is usually one of those charges, one of those atoms. So when it collides with it, during the collision, it's going to emerge in every direction that you can think of because of thermal agitation. So because of that, each charge carrier is moving in a random fashion. I'm sorry, this is already moving. So this one is moving this way, this one is moving this way, this one is moving this way, this one is moving this way. So my point in here is there is a large number of them, and if under no external E field, each charge carrier has a random velocity. So if I want to average what's the average velocity for all of them, which I'm going to call the drift velocity, then it's going to be simply in this case, which is the average of these random values, is going to be exactly 0. However, for example, if you go on top of a bridge or a freeway, it doesn't matter, the 91 or the 215 or the 10 or whichever, wherever you are close by, and you go on the bridge and you look at the traffic, for example, in that situation, you will notice that the traffic is moving in one direction more so than another. Okay, actually, as a matter of fact, it's moving uniformly in one direction. So what you start saying in this case, how many cars pass per unit time? So what you do in this case, you take for example 10 minutes and you start counting the car 1, 2, 3, 4, 5, 7. Let's say for example 20 cars pass in 10 minutes. Then you can do the math. You multiply that by 6, and then all of a sudden, why is this doing that noise? I don't have to do that meeting. Okay. Anyway, so we said we have 20 cars in 10 minutes. So you multiply that by 6, you have 120 cars per hour. So that is basically on that day, you have 120 cars passing that time. But if you go, for example, on the middle of the night, for example, on the same bridge, and you start counting the cars, probably you see 3 cars that pass in 10 minutes. And in this case, you say the flow of traffic at that time, you multiply that again by 6, 3 times 6 is 18. Obviously, 18 cars pass per hour. And like, for example, during the first time when you measured this, which was 120 cars that passed per hour, or yeah, something like that. So anyways, you can measure these quantities, and this is the drift with which the cars are moving. Now, if you go, for example, in a, I'm trying to give an example in here that is probably practical. If you go, for example, you know, for those kids rides where you have, or with those cases where you have those electrical cars moving every which way, and you find their average, they should be 0 because cars, first of all, are not going from anywhere from the arena, so they're staying in it. So on average, they're moving in every which way. So when you average the velocities and they collide with one another and they move back and forth and so on and so forth. So when you average, that quantity is 0. That is similar to this situation, except now when you organize the road, then in this case, there are more cars in here traveling. So let's say, for example, you have 120 cars passing per hour, and then you squeeze the lines. Okay, there is a construction or an accident ahead, so that now instead of 4 lanes open, you only have two lanes open. So if you want to squeeze the lines, there is a problem now, because now the 2 lanes will not carry 120 cars per hour, probably will carry less, that many. So the area now plays a role. It's important, the area in this analysis. It's like a hose of water. And let's say, for example, you have a huge amount of flow in that water, so when you squeeze it, and if you constrain the speed not to exceed its uniform speed, then obviously there is less flow per that area. There is more resistance in that case for the flow when the area is smaller versus when the area is wider. And of course, the length also plays a role too. So that is why these numbers are important. But what I'm saying in here, the random velocity should be 0 because it's random, because of thermal agitation. So there is no net drift. If there is a net drift all of a sudden by itself, then in this situation, hey, you have a current. So you need the net drift to have a current in this situation, okay? So this is the idea behind the electrical current. So what we're going to do now, we're going to apply an external electric field to this material. Remember, we're treating this electrons as being a cloud of charges, okay? Okay, let me give you an important point in here, very important point in the analysis. Let's say, for example, the charges are actually negative charges, okay? And apply an electric field this way. Obviously, the negative charges will be moving this way because F is equal to Q times E. And if Q is negative, then the force is actually opposite. So this is the force with which they're going to be moving, which is QE. Okay, I'm assuming E is in this direction. So if I'm monitoring the current is due to the charges moving in this direction. So if I'm looking at the cars, for example, all the cars are moving backward. That's all, okay? They're moving in the back direction. Now, if I apply the electric field still this way, so this is E, but the charge carriers now are positive. Okay? Then in this case, the charges will move in this direction because F equals to QE and Q is positive now. So the charge positive will move this way. for the same reason as the negative charges will move this way because of the same formula. If all I care about is the direction of traffic now, okay? Let's call this one is positive, okay? Direction. This is the positive direction. If the positive charges are moving this way, that is a positive current. So this is the current is actually moving forward in the same direction of the electric field, actually. That's what I meant with it. This one will be negative charges moving in the opposite direction as if positive charges, because if a charge was, let's say, for example, an atom in here has a positive and an electron next to it, okay? When this electron is forced by the electric field to move this way, now it's left a positive charge in here. So now the positive charge is net in here. So what happened in this case, this positive charge will borrow a charge from the next door neighbor and force that electron to move, come in here and replace it. So this motion of the actual motion of the charges, which is the negative charges, as if the positive charges are actually moving in the same direction in here. So if all I care about is the motion of positive charges in the direction of the electric field, I can think of the fact that the negative charges are moving to the left as if positives are moving to the forward, then they are actually the ions. As if the ions themselves are moving, but it's actually the electrons that are doing the motion. So this was confusion when we defined the electric field at the direction of the electric current and the electric field in the direction of the electric field, without really realizing that what was doing the motion was the electrons. So that's a convention only. So if I take an ammeter now and measure this device basically, and measure the current and have the needle point in here, because I'm thinking its positive charges are going to move this way, it's going to give the same reading for this material too, albeit charges are moving in the opposite direction because they are negative charges moving in the negative direction, so as if they are positive charges moving in the forward direction. So that is a very important idea in here. In other words, the current should not depend on the sign of the charge carriers. So we're going to build a theory and we're going to talk a lot of stuff in here. And at the end of the day, I will tell you exactly the summary, what you really need to know, okay? So we're going to get into a little bit of material science. So at the end, I'm going to tell you exactly what you need to do your homework and to do your problems. And even as an engineer, what is the most important thing for you, okay? But we really have to clarify those ideas. So this is an important point in here. What I'm saying in here is that the current that we're going to develop should not depend on the sign, okay? So if the sign is positive, the current should be in the same direction, even if the charge is negative. So we're going to see how that's going to work out. So it's an important point in here. Okay, so man, he's calling me. Anyway, so this is an important point, and we're going to come back to it, and it's very important that we are going to resolve this one. Now, how about the, we're going to define first of all what we mean by current. So the current, by definition, I is the rate at which charges are moving with respect to time. Okay, so this is the definition of the current. It's dq over dt. So this is what we mean by current. So if a charge is changing, I know we defined it in the case of the flow, how many cars pass per unit time. In this case, we're defining it in the case of the flow of charges. So how many coulombs pass per unit time. So that is really what the definition is. So if you're curious about the units of the current are the same units of a charge, which is a coulomb, divided by units of time, which is second. And this, by definition, is the ampere. Okay, and the ampere is actually a unit by itself. So in the MKSA system, this was the missing link. This is the meter. This is the kilogram. And this is the second. And this is the ampere. Now you have the picture is complete. This is the SI system. This is le système international. This is all the fundamental units that you need to know. So the ampere is actually a fundamental unit. The coulomb was not. When we defined it, we said that we're going to see the current, and that is going to be actually more fundamental unit than the coulomb. So the coulomb actually is a derived unit, and it's 1 ampere times 1 second. Okay? So this is actually a derived unit, and it's a combination of 2 units from the MKSA system. So it is important that you really have to have that in here. So the device that we're going to be using, and later on we'll get into this, the theory behind it is the ampere. So from this point on, the current is actually a fundamental unit. But the coulomb and the Newton and the Joule and all of the other units and the Pascal, they are actually derived units. They are not fundamental. They are part of the SI system, but they are not. They are not actually fundamental unit. Tesla is not a fundamental unit. Tesla is a derived unit. Okay, so that you guys know the Tesla for the magnetic field, we're going to see that down the road. Anyway, the magnetic field, which is volt over meter. Meter is fundamental, but the volt is not a fundamental unit. It's again in honor of Mr. Volta, but they are still, both of them are actually SI units. One of them is fundamental, the other one is derived. So the coulomb is not, okay? But the amp is, the ampere is. So that is a unit for the current in this case here. So this is the definition we're going to find here. So what we're going to do in this case, we're going to have to see how much current is flowing through this one when we apply an electric field. That's all. If these charges are drifting somehow due to an electric field, then I can find the current. This is how I'm going to do it, okay? We're going to see how they drift, but at this point, we're going to assume that somehow they have a net drift, okay? So here is the scenario. Again, I'm going to draw the material now, part of it. So we're assuming now that they have a net drift in here. So this is the drift with which they are moving, okay? So a bunch of them, not just one. There's so many of them, and they're all have a net drift, which is an average velocity with which they are moving. So this is not velocity for each specific charged particle. This is an average velocity. So the drift in this case is an average velocity. So it's not the velocity for each and every one of them, but on average, that is the velocity with which they are moving. So what I'm going to do in here, I'm going to come to this section here and wait a delta t amount of time. So this section is A, and wait a delta t amount of time and count how many charges pass by. That's all. So that is the number of charges that pass by times the charge. Each and every one of them is carrying a Q charge with it. So that's going to tell me how much charge actually passed by in that amount of time. And all I have to do is divide by delta t, and that is the current for me. So this is what I'm going to do now. After delta t amount of time, this charges that were in here will move to this location. So they are all here now. And this distance is v times delta t, that's all. So if they're vd, the drift velocity, I'm sorry, they're moving with the drift velocity times the time, which is delta t, and that is exactly how much they have moved. So how many charges did I count in that amount? All of the charges enclosed in here, in this volume. Since I know I have n charges per unit volume, all I have to do is multiply by this volume of this cylinder. This cylinder has a base A and a height v d times delta t. So the volume is clearly equal to the distance or the height vd times delta t times the area. And this is times n. So this is going to give me the number of charges now. So this is the volume now of that area, of that section. So in other words, I start now counting and how many charges pass by. After delta t amount of time, the charge that was here is here already, and one that is barely entering. So I count all of those inside this volume, and I know what the volume is of a cylinder. It's the area times the height, and the area is A. It's the same for the entire cross-section of this part of the wire, and then times VD times delta T. So that gives me their volume. But I know how many charge carriers per unit volume are, and it is exactly N. So this is how we define that. Oh, man, sorry about that. So that is how we define N. It's the number of charge carriers per unit volume, and it's a characteristic of the material. If it's copper, it has its own value. If it's silver, it has its own value, and so on and so forth. So now we have the number of charges, but each and every one of them is Q. So if I multiply it by Q, I have the actual charges now that passed by, that passed in delta T amount of time, okay? This is in Coulomb now, because this is in numbers per cubic meter. This is actually cubic meter cancels cubic meter, and this is a number times Q that is going to be in Coulomb. So now the current is this total number of charges, which I'm going to call it delta Q, by the way. So this is the entire charges where each and every one of them is Q, and this is their number in that amount of time. So if I plug in delta Q over delta T, that is going to be my current. So I is delta Q over delta T, and obviously delta Q is equal to Q times N times VD times delta T times the area A divided by delta T, and cancel the delta T everywhere. So it doesn't matter how long it takes. Even if I do it in 1 second, it's the same thing. So the lapse of time doesn't matter because it's going to cancel out anyway when I'm finding the current. So the current, if somehow the charges drift, is equal to Q times N times their drift velocity. So this depends on the drift velocity. So if the drift velocity is 0, there is no current. End of the story. So if these charges do not drift somehow, if I just rely on the random motion due to thermal agitation, these things will not have a current. They will move every which way, and this average will be 0, as mentioned before. And you will not have a current under normal circumstances unless somehow you're going to push the charges to move on average in one direction, in which case you will need probably an electric field to cause that. When you do that, then you have a current. But at this point, it depends on that VD. It depends, of course, on the number of charges that you have in there too, that are available for the material. Depends on how wide the area is. If the area is too narrow, in this case, I is small because you can't have, there is more resistance when the area is small. If the area is wide, of course, you are going to have a wide number of charges that can pass through it. As a matter of fact, we have another quantity. So this is the current, by the way, which we're going to need for some of the problems from this chapter. Okay, we're going to define another quantity now, which we're going to call Q for the sake of problems is E, okay? Q in magnitude is equal to E, which is 1.6 times 10 to the negative 19 coulombs. So if you're going to do this problem, this is the value of the charge carriers in the normal conductors is just the electrons. And this is their charge value in this case. Okay, anyway, we did not solve some of the questions related to this one because we don't know what VD is yet. So we have to find what that VD is. So before we do that, I'm going to define a new quantity called the current density, which is going to play major roles down the road in chapters 28 and beyond. Okay, current density. And that by definition, J is going to be equal to I over A. So what I mean by that? I mean, because if I make the cross-section smaller, I will have less current going through it. If I make the cross-section bigger, I will have more current going through it. So what I care about now is the current per unit area that passes. And that way now the area effect is eliminated completely. So the properties of the material now becomes more relevant when we're studying the current density, not the current itself. So the unit for this guy is going to, of course, be amps per square meter, okay? So that is really what the current density is. So what we're saying in here is ignore the area when we're talking about this problem because we want to trivialize, make it trivial, the area by introducing a new concept called the current density. And that current density now renders the area useless because as you can clearly see from this expression, the current density J or I, however you're going to write it, is actually J, I'm sorry, capital J. Why did I? It's capital J, is equal to, the area cancels, and it's just simply equal to the charge carriers, Q times N times VD. That is the whole point of introducing the current density, so that this problem becomes a little easier because then we're actually focusing only on VD, trying to find what that VD is. So let's find what that VD is. the drift under an electric field. So Mr. Ohm said the following, basically. He argued the following, and he actually showed it experimentally, that the current, if I apply an electric field in here to the wire, charges start to drift one way or the other. And this drift must be proportional to the electric field, because if I don't have an electric field, I don't have any drift. So that is basically in a nutshell. How fast, how much current density I'm going to have depends on the material, that's all. So this is what he said. He said that each material has a characteristic value, which he called it the conductivity or resistivity, depending on how you define it, where J, the response, is equal to E, which is the cause, divided by rho, which is a property of the material. This is, he called it resistivity. Okay? So this is what caused the electrons to move anyway, which is that VD, okay? To drift. That is the electric field, and this is the response of the system. Alternatively, this expression is written as sigma times E, where sigma is the conductivity. In other words, you can relate sigma and rho like this, okay? Meaning that there are some materials that have high resistivity. That means that you will have hardly any current density whatsoever, even if you apply an electric field to them. Those are insulators. There are some materials that have very low resistivity. That means even if you apply a little E, you're going to end up with a big J, big current density, and vice versa. Some materials the same materials that have very high resistivity, which are resistors, they have very low conductivity. That means that they are poor conductors. So this is an important analysis from this relationship. Good conductor is actually a bad insulator. Same thing, bad insulator. And opposite to that, actually, a bad conductor is actually a good insulator. What I mean by good and bad in here doesn't really mean negative or positive. It doesn't have any kind of bearing whatsoever. Sometimes you're actually interested in conduction. So you want a material that conducts. You want copper, for example. This one is important. Sometimes you're actually interested in insulation. You don't want charges to leak somehow and cause problems for your circuit, and you want an insulator. So both of them are actually needed in electricity and magnetism. So you can't really have one without the other. If the air is somewhat a good conductor, we will have a problem where we are, because electricity will be flying every which way and no device can stay still. I mean, everything will be in big jeopardy, including electronics and ourselves and everything. So again, sometimes you really are after good insulators, so you're going to have high rho. Sometimes you're going to actually go after good conductors, so you're going to have low rho or high sigma, okay? Please do not confuse these symbols with what we did so far for the charge density per unit area, where we define sigma is equal to Q over A. That has nothing to do with it. And also where we define rho as being Q over V, that is the charge density, where we defined it per unit volume, and this is per unit area. Or when you guys did in physics for A sigma as being mass divided by area, that too actually the mass divided by, that is not have to do with the sigma or that sigma for that matter, and where you define the rho actually in that time too as being mass per volume, and that was the density, what we call normal density of the material, which I referred to earlier when I was talking about N in this case. N has to do with the density. That was that mass divided by volume. So that is actually stuff from previous chapter. This is actually the item of the discussion that I want you guys to have it clear in front of you, the distinction between the symbols. Okay. Physicists really in the context, they know exactly which value you're talking about. What are you referring to? Okay. They don't need any more clarification. Is this clear?
Yes. I was thinking for a minute that I'd seen sigma somewhere. I was about to say what were the differences, but yeah, it makes sense now.
Very good. So please pay attention to this little details, because sometimes they can throw you off. And you have a homework problem or you have an exam problem. And since this is an open text, open book exams, you're going to be tempted to use the wrong formula and you end up with some nonsense stuff completely have nothing to do with this, the problem that you have before you. That is because you need to make that distinction. You need to really be aware that the symbols in this time, in this case, are just symbols. They refer just to stuff. Here is what they refer to in this case. This expression here, conductivity here. How a system will respond to an excitation, in this case, the electric field, and what kind of conduction you're going to have, okay? So this is Ohm's law. This is really what Ohm's law is all about. This is not what you see in textbook. If you go right now and Google Ohm's law, this is not probably what you're going to see. This is not what people or engineers or even physicists refer to as Ohm's law, because there is another law that derives from this one that which we're going to get to very soon. So let's see how that works in this scenario, because we want to get to this expression, because we want to use this VD here, okay? So let's see now. So what happened in this case is the following. So I'm going to redraw one more time the wire. I'm going to assume that there is an electric field now here, and the charges somehow are responding, and I'm oblivious to their sign still. They're going to respond to this electric field by going F equals to QE. Okay? Actually, this is a vector relationship, and so is J, by the way. J is a vector and E is a vector. Rho is a scalar, okay? The current density is actually a vector. It depends on the sign in here with which VD goes, okay? So this is Newton's law, tells me that these charges, if they have a mass M, then in this case, this is MA, okay? From here, I can find what the acceleration is of these charges. So these charges will be subject to an acceleration, which is just QE divided by M. So these charges already have random motion to begin with before I start applying the electric field. So they are moving somewhere. This one was moving this way. This one was moving this way, and so on and so forth, okay? This one actually was moving in the opposite direction. So when I apply an electric field, so this becomes like your initial velocity. So this one now will go this way, try to turn. This one will actually accelerate more. This one will stop and move back. This one will turn this way and continue now moving. So everybody now start to align more or less with the electric field. So that is basically a nutshell in here, okay? What's going on? So if I integrate this, Q is constant, E is constant, and M is constant. So if I integrate a constant to find the velocity, then this expression, because this is still dV over dt. So I get the V, the integral of a constant is just a constant times time, plus that random velocity, which is the initial velocity during that stage, okay? Here is what I'm going to do. I'm going to average this quantity. I'm going to average this quantity. Once I average this quantity, this is going to be the drift velocity, because the drift velocity is the average velocity with which everybody now is moving, okay? So when I average this quantity, it's not going to be zero anymore because of this quantity in here. So V average, which is the drift velocity by definition, is going to be simply equal to QE over M times an average time in this case, plus zero. The reason why I'm saying zero, because this is random anyway. So when you average, it's going to be zero because of thermal agitation. So there is a time in here that is an average, and I'm going to see what's going on with it. When the electric field is applied, you have a charge in here. Now, all of a sudden, all of that is moving with a drift velocity, okay? And it's going to move this way. The other one I'm going to ignore it because it's average to zero anyway. So this one will move until it collides with an ion. So this Q now will move until it collides with an ion. So once it collides with an ion, it's going to come with every single way possible. So that is going to be basically a new initial velocity now for the next stage, in which case it's going to have a new average velocity, and then it's going to drift with that everybody's average velocity until it finds another ion in here. Okay, obviously sometimes it's going to find it very soon. And sometimes it's going to find it very later. Okay, so this time now, which is this one, and this time, which is shorter, and this time, which is longer, is what I meant with it as being the average time between collisions. Tau, which is the average time between collisions. That is really what we use in this case. So if the average time between collisions is very long, that means it has a long time for it to gain a lot of velocity because it's accelerated during that time. Obviously, the velocity will be higher because it's going to be higher too because of tau being too big. So the drift velocity is directly proportional to this time. So VD is still equal to QE over M times tau, okay? Because the other quantity is 0 anyway. So what's going on in here? If tau is very big, that means there is a long time for it to accelerate and gain a lot of speed. If tau is very small, it accelerates, but then bumps into an ion, it's going to hardly move because every time it comes up in a random velocity, so it's barely going to move. So this tau is really the one that determines a good conductor from a bad conductor. If tau is a long time between collisions, that on average, of course, then we have a good conductor. If tau is actually very short time between collisions, we have bad conductor or even an insulator at times, okay? So tau is the one that determines the conductivity. M also plays a role. M is a very important quantity here that plays a role because the charge, for example, of the electron, mass of the electron is 9.1 times 10 to the power negative 31 kilograms. And that of an ion is typically, the mass of an ion is typically of the order 10 to the negative 26, sometimes 10 to the negative 25. Because this number is actually roughly 10 to the negative 30. This is actually 10 times lighter. Oh, no, I'm sorry. Yeah, 10,000 times lighter on average, okay, than ions. They're 10 times heavier, I'm sorry, more heavy. So they have a lot of inertia ions. So they don't really move that well versus the electrons which are lighter. So that's why really what causes the conduction in materials are actually the electrons because of this fact, because of the M is in the denominator. So now if I take this value of VD and plug it in the expression that we found for J, which is N times VD times Q, this expression, then VD times Qn will give me now the actual current density. So the current density now, which was equal to N times Q times VD, just plug in the value in here. So I have NQ times Q times E over M times tau. Obviously, this expression has so much to tell us. First of all, J is proportional to E. So E now is on the other side. Now, what I have in here, I have N times Q squared times tau divided by M. So sigma then, the conductivity is equal to NQ squared times tau over M, or rho, if you wish, is M over N times Q squared times tau. Meaning, more massive charges, so we don't care about that, so it's only electrons. Q is, regardless if it's positive or negative, it's squared anyway. So now the conductivity or the resistivity do not depend on the charge of the sign of the charges as we expected, as we hope to see, should not. That was a hope, actually, depend on the sign, and it does not, because when you square this quantity, it's going to be positive anyway. Obviously, it depends on how many charges you have in the available. The more you have, the low rho is. The more valence electrons that can participate in the conduction, the more you're going to be in good shape. But that is a fixed number. Usually you really don't have a lot of control of it. So this is where you play with things. The longer the tau, the lower the rho. That means the lower resistivity, the higher the sigma, the good conductor it is. That is really what determines it. The shorter the tau, the shorter the time between the collisions, the higher the rho, the higher the resistivity, the lower the sigma. So if tau is short, that means sigma is very small. So that is really the theory behind it. So for you, for your homework problems. For everything else, what matters? This expression matters sometimes, at least for this chapter. Doesn't really last with you as an engineer. You don't care for this expression that much. You care about this expression because now you assume that sigma, you can somehow find it and you have a justification for it, or rho, you can have a justification for it, okay? And this is justification behind it, okay? So if you are an engineer, those expressions you don't really care very much for. So hopefully you guys have picked up on this. Rho or tau, both rho or sigma, for this case, they depend actually on temperature, in such a way that rho is some fixed number times 1 plus alpha times delta T. If temperature increases, rho increases with it, and that is because this alpha now is actually a fixed value that depends on the materials, okay? This is for small changes in temperature. So this is an experimental, this is an empirical law. That has a justification in thermodynamics, but this is basically the topic here. So this is the resistivity at room temperature. This is resistivity at room temperature. And this is the change in temperature. Usually it's T minus room temperature, T naught, where T naught is room temperature. Okay, this value is actually in degrees Celsius or Kelvin, whichever you like to do, okay, it doesn't matter. Alpha in this case is specific to the material. Coefficients of thermal conductivity. On the material. Thermal conductivity. No, not thermal conductivity, sorry. Electrical, what is it? So it's specific to a material. I don't know what the exact name for it anyway in here. Resistivity as a function of temperature. The unit for it is 1 over Kelvin or 1 over degrees Celsius, okay? Times, of course, the units for rho naught, which will, no, just basically 1 over temperature only anyway. So this expression you might need for some of your homework problems. That's why I'm mentioning it in here. This is important in terms of lab too. If we're doing this lab on campus, is a very important idea because this is what's going on. You take a resistor, for example, and you connect it to a battery and you start doing measurements. Well, a resistor in this case will start to heat. When it heats, its resistance will change with time, with temperature, that is. So you have to be very careful because the next measurement, you will have a different value for R. It's not the same thing. So it's changing with the temperature. So you have to be very careful and mindful of this expression, not to allow the temperature to change that much, because if it does, and you can touch any device that is connected to a plug, and you will see it warm, hotter. And that is because of this. Get your hand closer from a light bulb, and you will see actually the heat there that's coming from it. Because it's essentially, that's a resistor to its conductor too. So any conductor, after a while, it gets warm. And we're going to talk about that one, which is called the Joule heating, which is important, which we're going to explore very soon. Anyway. So this is what some of the importance in here. So for doing lab, we have to be very careful with this expression in here because it might alter our answers. And we might get a lot of errors because of that, okay? So let's go now to a very important expression of Ohm's law, which is very important. So what I'm going to do now, I'm going to take back my wire of cross-section A still and apply an electric field to it, E. So now I'm going to have a current now that is J equals to 1 over rho times E, okay? That I know. This is basically where rho is given by that expression in here, M over NQ squared tau. By the way, this is just a model. That's why I'm not really making too big of a fuss of remembering all of these details, because actually this thing involves really quantum mechanics and there is other things at play too. But this is a model that can explain a good conductor from a bad conductor. In other words, when you are at the extreme ends, this is actually a good model. But when you are in the fuzzy zone, like for example, semiconductor, this will not work. So you'll have to invoke quantum mechanics there. Anyway, so this is basically Ohm's law, as I was talking about in here. The electric field and the current density, they are proportional to one another, and the constant of proportionality is exactly 1 over rho. So let's take this material now, and try to find the potential. Let's say, for example, V is equal to 0 on this side, and V is equal to some value in here, which is V. That is what causes the electric field in here to move this way. In other words, there is a battery in here where this is a positive, and the same thing in here, there is a negative. That causes what causes the electric field for the charges to move this way. So there is a higher potential in here and a lower potential in there. So this is a V. So what I'm going to say in here, this is X equal to 0, and this is X equals to L, which is the length of the wire that I'm studying. This is L, okay? So if I'm careful with the calculation, all I'm going to do is integrate this value, and I will find that V is equal to EL, really. V is equal to EL. Similar to the capacitor when we did the capacitor. This is no hard because E is just the derivative of V with respect to X. And when you integrate E, which is constant, assumed to be uniform, you're going to integrate the constant. So it's going to be E times X, integrated from 0 to L. And this is going to be just V equal to EL. So we went through this exercise before in the past. dx is in this direction. E is in this direction. So the dot product of E times dr is going to be minus E times dx. And don't forget that this expression really between E and V is minus dV over dx. So minus and plus is going to cancel one another. So when you introduce V, so it's going to be minus times minus is going to be plus. And the expression is correct. V equal to EL, basically. Between end to end, though. The entire length of the wire, okay? So in other words, the electric field from this expression is going to be simply V over L, okay? So I'm going to plug that one in here. I'm going to also note of the fact that the current density and the current are related to one another as this. I'm sorry. I is equal to JA because we define J by definition as I over A. Remember, when we trivialized the problem, we said ignore the area. Let's introduce a new J now. Instead of dealing with the current directly, we're going to deal with the current density. So this is the definition for J that we used then. So now that value of J, which is I over A, I'm going to replace it in here in this Ohm's law. So it's I over A really is equal to 1 over rho times E. And E is actually V over L. What this expression look like then is V is equal to rho times L over A times I. This looks like V is equal to a constant R times I. V equals to Ri, where R depends on the geometry of the material, which is L and A, and depends also on its resistivity, which, if you want to, it's this expression that depends on internal properties. The charge carriers, their mass, the charge per unit volume for that material, and the time, the average time between collisions. So this is the material, rho, and this is the engineering part of it. How long do you want to make it, and what's the cross section of it? So basically, R takes all of these quantities and sweep them underneath and give you a definition for it. So where R in this case is rho L over A, okay? So this expression you will need big time for your homework, okay, and potentially exam. And this one is by far, far more important. I promise you to tell you in a nutshell what's going on. This is what people refer to as Ohm's law. But it's really not really the Ohm's law because it's derived, as you can see, from really what Ohm's law is. This is Ohm's law. But if you follow this logic, you're going to find an expression for it, V equal to Ri, okay? To the extent that now, if you tell anybody Ohm's law, they tell you V equal to Ri, where R is the resistance. R actually is measured. R, the units for R are measured in the units of the voltage, which is in volts, divided by the units for the current, which is amps. So this is volt per amp. But in honor of Mr. Ohm himself, we gave this one the unit of capital omega, and we read this one as ohms. So this is capital omega, and it's read as ohms. So that is the unit for measuring the resistance. So this is the resistance. This is what this means now. If I have, this is how I will write it usually. if I have a voltage, I will get a current that is inversely proportional to the resistance. The more resistor the object is, the less current I'm going to end up with. The less resistant the object is, the higher the current is. So this is actually a one-to-one correspondence. As a matter of fact, if I plot this expression here on a graph, usually we plot the x-axis as being the current and the voltage as being the y-axis, which is really backward. It should be the other way around, because this is actually the cause and this is the effect. This is the independent variable. This is the dependent variable. But if we plot it backward, this is how this graph would look like. It looks like it's a line, Ri, okay? In other words, this is a line whose slope is exactly the resistance. That's why we like to graph it this way, okay, backward. So this is the tangent of this angle is exactly what R is, okay? If a circuit behaves this one or component behaves this way, we call this behavior ohmic behavior, ohmic device, okay? If a circuit does not behave in a linear fashion, we call it a non-ohmic device. Like, for example, this one, which I'm going to draw quickly. This one is a non-ohmic device. Anything other than a line is non-ohmic. This is actually a diode. It's actually a semiconductor, actually. This one has that behavior. The one I was talking about, the one that I was drawing, the second one. So it actually goes exponential with voltage. Actually, I drew it backward, I'm sorry. It goes like this, okay? Because the voltage is on here, so backward, okay? Anyway, it's non-ohmic, it's still no good. It's not a line anyway, but you need that, actually. You need that for other devices, okay? You need non-linear devices like this one for circuits, okay? So anyway, so this is basically what Ohm's law is. Okay, how are we doing on time? We still have good time. So let's cover a couple of items in here, and that is the symbol for a resistor. Is like this. So if you see this symbol, usually with the value of the resistor next to it, that is what a resistor is. For example, this could be 10 kilo ohms for all we care about, okay? Or 5 ohms or 6 ohms, it doesn't matter, okay? So this is a resistor. So now we have a bunch of stuff that we can work with. We have capacitors, we have batteries, and we also have switches. So we can do stuff with these things now. We have a little bit of more things to work with. Before I do that, let me talk about a couple of things. Resistors in series. So this is what I mean. Remember when we did in your notes, this is what I want you to do, okay? I want you to reserve a whole section and draw this table. On one line, you're going to say series, and the other one, you're going to say parallel. Okay? In here, you're going to talk about capacitors that we did already. And in here, we're going to talk about resistors. I want you to leave another one in here that for right now, you're going to call it inductors. So when we get into that point, we're going to refer back to this table. Okay? For my notes. So we're going to come back in here and hopefully I will remind you of this device, of this table down the road once we reach inductors, okay? So what's going on in it? So for the capacitors, if I have a bunch of capacitors and I want to connect them in series, if you guys remember, the C equivalent was 1 over C equivalent was equal to 1 over C1 plus 1 over C2 plus 1 over C3 and so on and so forth, okay? When they're in parallel, then in this case, the equivalent capacitance was C1 plus C2 plus C3 and so on and so forth. Let's see what's going on with the resistors, okay? When they're in series and when they're in parallel, both of them. So I'm going to take this resistor now and connect it with another resistor. So this is R1, and I'm going to take another resistor now and call it R2 you connect them to a battery and switch and everything else, okay? At some point, I am concerned with this point in here, concerned also with this point, which I'm gonna label 2, and the point 3. So what I'm saying in here, the voltage between 1 and 3, which is V1 minus V3, that is how much voltage I drop going from 1 to 3, is actually equal to V1 minus V2 plus V2 minus V1. Does this expression make sense to you guys? Yes?
Yeah.
Okay.
Kinda.
That's, look, V1 minus V2 plus V2 minus, I'm sorry, V1, sorry, V3. What am I talking about? Yeah, does it make sense now? I'm sorry about that.
Okay, now that makes more sense.
Okay, very good. So when we get into loops later on, Kirchhoff's rules, we're going to do actually V1 minus V1 at the end. We're going to start from one point and come back to it. So at this point, we're starting from one point and coming to the other one. So it's like a difference in heights and buildings. And we did this discussion when we were doing capacitors. The voltage drop in here, this is the voltage between 1 and 2. That is actually R1 times the current that is flowing through the circuit. So there is a current now, I. And the current must be the same current in here. The reason why it has to be the same is because there is a conservation of charge. So if there are 10 coulombs that pass per unit time, then the same 10 coulombs must emerge from here and there too. So the current is the same everywhere. So that is actually another way of saying what series is. So I is the same. So when you see I is the same or Q is the same, that is series. So in this case, this quantity is actually equal to R1I. And this quantity is actually equal to also R2I, because it's the same I going through both resistors. And this voltage drop between 2 and 3 is actually R2I. So this is actually plus R2I. And this is equal to the voltage drop between 1 and 3. So the voltage drop between 1 and 3 is just R1 plus R2 times I. From another point in here, I can look at this entire thing as just one big resistor as equivalent to both resistors, because from point 1 to 3, all I have is I have a current flowing through it, and they have an equivalent resistor that produces the same effect. Obviously, R3 times I will require, or R equivalent, I'm sorry, R equivalent, will require that R equivalent would simply be the sum of the resistors. That's all. So in this case, when they are in series, the equivalent resistor is actually the sum of all of the resistors, is R1 plus R2 plus R3, and so on and so forth. This is unlike the capacitors. The capacitors were the inverses of the sums that gave me the equivalent inverse of the equivalent capacitor. For the resistors, no. When they're in series, it's actually like when you had in parallel, actually, the capacitors. So that's why this table is very important, that you guys need to refer back to it when you're doing your problems, okay? Let's take now the case of the parallel circuits. So for the parallel, what I'm going to do now, I'm going to take two resistors, R1, and another resistor, R2, and connect them in such a way that their ends have the same voltage. Again, when I say parallel, V is the same. So the voltage going from this point to that point is the same voltage as going from the other point to the other for R2. It's the same voltage. So if they connect them to a battery, I have a current in here, I, that need to split itself accordingly in this junction in such a way the current I1 goes through this one and current I2 goes through the other way. The only reason for these two currents to be the same, because the voltage between 1 and 2 is the same, which is V1, 2, is on one side, it goes through this current, and on the other side, it goes through the other current. So it's really I1 times R1 or I2 times R2. So the only reason for these two currents to be the same if the resistances are the same. The sum of those two currents, because of the conservation of charge in here and the junction, it splits itself between I1 and I2. Clearly, I is simply equal to I1 plus I2. As if between I1 and I2, what I have actually, I also have an R equivalent between 1 and 2 in such a way that the voltage between 1 and 2, which is V1, 2, by the way, is equal to this R equivalent times I. Okay. So what I'm going to do is I'm going to find I1 from this expression, and I'm going to find I2 from this expression, and I'm going to find I from that expression and sub them into this one. So from this one, I have I1, which is V12 over R1. I have I2, which is V12 over R2. And I have also I, which is the same voltage, by the way, between 1 and 2, V12 divided by R equivalent. And I use this expression now to write I, which is V12 divided by R equivalent, is equal to I1, which is V12 divided by R1, plus I2, which is V12 divided by R2. Cancel the R1, the V12 from everywhere, and we find that 1 R equivalent is equal to 1 over R1 plus 1 over R2. So in other words, for the case of the resistors, when they are in parallel, the equivalent resistance is going to be equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on and so forth. Okay? So this is basically, in a nutshell, how this is working. One final item in this chapter, and we would have covered it completely, okay? And the item, the last item. So there is a question mark in here, so don't fill it out yet, okay? For the inductors, we're gonna come back for the inductors down the road, okay? And this is gonna be way after exam one. I mean, after the midterm. When we get into that, I'm going to refer back. That's why I put the comparisons in here for me to remind me next time when we meet to come back to this table so that we are going to fill the rest in here, okay? So this is something important because we have devices that we can connect them somehow either in parallel or in a series, okay? And today we're going hopefully to get to an example like that. So let me explore the idea of the energy because it doesn't really matter until you talk about power or energy. Let me go back one final time to my wire, okay? So I have in here V between 0 and V, that is a potential difference. And now what I'm going to do, actually, I'm going to see how much energy required to move an element of charge through this potential. So the energy in this case is going to be equal to du is simply going to be dq times the voltage difference, that's all. And the voltage difference is, if you guys remember, it's Ri. So V in general, okay? Because the voltage is fixed, so when I integrate that expression, it's going to be Q, but I don't really know how many Qs are passing over time. So this is energy that is going to be dissipated over time. But instead of doing the energy, we're going to deal with the power, and the power simply, so this is the power, and the power simply is du per unit time. So this is clearly dq over dt times V, and this is the current, I. So the power is equal to VI. So in the case of the circuits, the power is equal to VI. And V, if you guys remember for a resistor, it's Ri times I. So this is the power dissipated, the power of energy dissipation per unit time. This is exactly what I was referring to earlier. If you leave your device connected for a long time, it's going to get warmer and warmer because of this way. The power is being dispersed in the form of heat all the time at this rate, Ri squared. So it matters which current you have in the circuit in there. So if you have a high current, there is far more dissipation of power than if you have a low current. So this is called the Joule heating. So that's why if you're doing this experiment in the lab, you have to be very careful with your experiment because there is heat that is associated with that. Light has a light bulb that is made up of actually resistors. And if you bring your hand closer to it, you will feel the warmth of it. So that is basically what we're talking about. So it's dissipated in the form of radiation that is actually in the old incandescent light bulb. So basically what's going on in this case is going to have so much power dissipated that actually the temperature will increase so much that light glows from it. And that is the yellow light you see from old light bulbs, okay? So that is basically how energy is dissipated in this case. It's a very important relationship. So in terms of what you have to remember for your exams or homework and things like this one, it's this one. Remember for the capacitor, it was an energy that we found, which was Q squared over 2C, okay? And the energy also was expressed in terms of the terms of the voltage of 1/2 of CV squared. But that is an energy. In this case, we have a power because we have current. We don't really have charge. So a current is the rate at which things are moving. So in this case, we still have a rate of energy, not the actual energy. It's not the actual energy. So that is a difference between the two, capacitors and a resistor. In other words, if you shut down the current, it's immediately going to go down. So there is no energy stored in a resistor. It just basically dissipates energy. So it's a wasting device in terms of energy when it comes to it. So we still have about 10 minutes. I'm hoping to get at least one example through. By the time we meet next time, we're going to finish the other two examples, or at least discuss one of the other examples, and then do another problem. And we move on to chapter 26, okay? Oh no, this is not the page. So I'm supposed to be doing chapter 25. And the two examples, first of all, problem 59 is identical to those who are sitting in physics 4C, to a problem from chapter 17, which is problem 113, okay? So I'm gonna have a brief discussion on that problem 59 in this class. And if you're interested about solution, I'm going to refer you back to that video from that class where I made 2 mistakes in that problem, but I'm gonna refer you to it again because heat conduction and electrical conduction are similar when it comes to that specific formula. So, and the calculation are identical, okay? We're gonna talk about that problem, so chapter 25. And then I am going to do, I think problem 71 is the one that I decided to, problem 71, and potentially another problem, so I didn't decide yet on it yet. So let me get into chapter 25. So problem 71, okay? Still have 10 minutes, well, almost 10 minutes now, 2 minutes left. So it's a good idea to draw your circuit, okay? And let's talk about problem 71 and how it looks like. So the problem we're going to do now is 71, by the way, okay? From the 15th edition. So problem 71, it says in here, is consider the circuit shown. The EMF source has negligible internal resistance. The resistors have resistance R1 is equal to 6 ohms and R2 is 4 ohms. The capacitor has capacitance of 9 microfarads. When the capacitor is fully charged, the magnitude of the charge on its plates is Q36 microcoulomb. Find the electromotive force of the battery, find the voltage of the battery, basically. So this is how the circuit will look like. So you have a battery in here with its own voltage E, okay? And you have a resistor in here. This is labeled R2. And you have another resistor in here, labeled R1. And now, usually, technically, you really need a switch, but for practical purposes, you really have to have a switch, okay? And then you have a capacitor in here, which is C. If you look at the drawing, this is how this is drawn, okay? They tell you R1 is equal to 6 ohms, R2 is 4 ohms, and C, the capacitance, is 9 microfarads. Okay, they tell you after they close the switch, or they basically when the capacitor is fully charged, so you close the switch and you wait a long time. They didn't draw the switch in here, so you wait a long time. So there is a charge Q now on this capacitor, and this charge Q is equal to 36 microcoulombs. Okay, and they want to know what this value is. So this is what we're going to do. Once this is fully charged, it really acts like an open circuit. Once it's fully charged, there is no current that is going to fly through it. So I on this side is exactly equal to 0 at that point. So how much voltage drop in here? The voltage drop across the capacitor is simply equal to Q over the capacitance, that's all. So the voltage drop across the capacitor, which is in parallel with R1. So the voltage drop across the capacitor and the R1 are the same voltage. So if I find this voltage drop in here, I can't really draw it as an arrow because it's not a vector. That's the direction of the electric field. But this V, C, and this is if it's 0, which is 0 everywhere, by the way. then in this case, this is VC. So its value is equal to Q over C. And I know Q, and I know C. C, by the way, it's 9. Okay, so my 9 and Q, sometimes they look alike, okay? So in this case, VC is equal to 36 microcoulomb divided by 9 microfarads. The micro and the micro cancel, which is good. 36 divided by 9, that's 4 coulomb over farad, that is volt. So it's 4 volts, okay? So we know this voltage is 4 volts, and it's the same voltage across R1. R1 must have a current flowing through it now. And this current is the same current that is flowing through R2. So the current comes in here, nothing goes to the other side because this is fully charged. It's not gonna accept any more charges, okay? So in this case, the current must flow of its entirety by conservation through R1. Once it reaches this point, it cannot go this way either because this is fully charged. It cannot take charges from either way. So the current must go back through the battery. So the current I is the same current flowing back in here, and the battery will push the charges back and forth in here. So let's find now this current. Because the voltage drop across R1 is equal to 4 volts, because they are in parallel, by the way. So this is 4 volts. This must be also be 4 volts. It's not the same value as in here because I have an R2 now. I cannot really say that. Actually, the value is epsilon now. So the voltage across R1 is the same as the voltage across capacitor because they are in parallel. That's why, okay? And this is 4 volts. And this one is equal to R1 times I, which is the same current that flows through everybody. Not this I, by the way. This is I through capacitor, okay, which must be 0 when it's fully charged, okay? So the same I in here that goes through R2 though, okay? So from here, we're going to find what I is. This is 6I. So that means I is equal to 4 over 6 amps, okay? So that is the current that is flowing through that part of the circuit, okay? Equal, not minus, okay? 6I, because R1 is 6 and I is I. So you divide by 6 and you find the current. So this current is going through also R2, and they must be now in series because they have the same current. So R2 and R1 actually in series. So R1 looks like it's in parallel with this one because they have the same voltage, but in the same time, it's actually in series with this one because they have the same current. So in the same token now, what I can say is the EMF in this case must be equal to R1 times I, or R2 times I, plus R1 times I. And since I know what R2 is simply equal to 4 ohms. So this is 4 times 4 over 6 amps plus 6 times 4 over 6. And the common denominator is clearly 6. I don't want to do simplification. 6 times 4 is 24 plus 8. What is it, 32? What is 32 divided by 6?
Isn't that 4?
No, 16, I'm sorry, 16. 16 plus 24. That is actually not 32, sorry. That's when you do sometimes stuff fast, you're going to end up pay for it dearly. So I really have to, so I have 16 plus 24. Is that 40? I don't mean this 40. I don't mean to write it this way at all. I mean to write it with this device. Okay, let me be careful in here because I really don't want, I know we're rushing things and we have 1 minute left. So what I have in this case is 4 times 4 plus 6. Yeah, I mean, it's clearly 10 times, when you take 4 as a common factor in here, it's 40 divided by 6. So it's 40 divided by 6, which is 6.67. Volts, because I have an ohm times amp, that is a volt, okay? So 6.67 volt, and that is the current flowing through all of them, actually. As a matter of fact, I can check this value and find it in here and find the entire thing and find the voltage drop because we know 4 volts in here. This is 4 volts. We know this is 6.67 volts. How many volts in here? It should be the difference. 6.67 minus 4, it should be 2.27. So this should be R2 times I, and R2 is actually equal to 4 times I, which is 4 over 6. So this is 16 over 6, and is 16 over 6 equal to the difference between 6.67 and 4? So 16 over 6 is 2.67. Oops, is 2.67. Obviously, if I add up 2.67 and 4, I should have the voltage of the battery, which is 6.67. That is how we check actually our work when we're doing problems with circuits. We're going to have a lot of problems with circuits. So if you don't understand this example, don't worry. We'll have far more examples with circuits. I think, like I said in the beginning, when we started this portion of the class, that my students usually like circuits more because they seem to be in control of them. So I'm hoping that you guys will enjoy them too, okay? So we're going to discuss problem 59 and problem 70 and potentially another one depending, okay? But we're going to jump also to chapter 26 comes Thursday, when it comes to Thursday, when we meet next time, okay? And we have lab, of course, which has also have to do with this stuff, Ohm's law and verification of Ohm's law and things of this nature. Any questions?
Yeah. Yeah. So I had a question toward the example that we did, specifically how we got the 6 under.
Hold on. Let me share with you the screen so that we're on the same frequency.
Mm-hmm.
Okay.
So
where did we?
Okay. Yeah, so when we got VR1 equals VC equals VR, and then we got 6I, how did we get that? That's kind of where I always got lost.
That's R1I.
Right.
R1 is 6 ohms.
Oh, okay.
R1 itself is 6 ohms times this must be equal to 4 volts because the same here of 4 volts is the same drop in here. But I know the value of the resistor being 6 in here, 6 ohms. That's what they told us in the problem.
Right.
Multiplying I to furnish that value to make it 4 volt because we know it's 4 volts as being charged over capacitor on one side. So it must be current times this resistor also must be 4 volts because both of them are in parallel from this configuration. So the same voltage, whether we look at it from this point to here or this point in here, these 2 points are the same. Actually, this whole area is the same wire. Okay.
Okay.
Same thing. This whole thing is the same wire. So if I look at it, this is 4 volt, which I can calculate because they tell me specifically the charge is 36 microcoulomb and the capacitor is actually 9 microfarads. So we know from previous chapter 24 or before that, that this must be the voltage drop is Q over C. And Q is 6 microcoulombs and C is 9 microfarads. So I know what V is. So it's all a matter of finding what that I is.
Okay. Yeah, now it makes sense.
Very good. Yeah, no, those questions are typical. So please do not hesitate to ask these questions because they will help you overcome these problems because when you're doing these circuits and we're gonna, like I said, you're gonna be fed up with these things, okay? From chapter 26, you have plenty of examples, hopefully, so that you can look at a circuit and you start working with it. As promised, there is actually another component that we will be dealing with at some point in the future, and that involves time actually in it, and those are inductors, okay? Inductors, they're not really going to be that much a problem because this is going to be DC circuits. This is a DC circuit, so this is a battery that provides DC current, which is continuous current. This current doesn't change. It's 4 over 6 amps, end of the story. But down the road, we will have AC currents, which involve these guys, okay, the inductors. So that's why this table is not complete. Good?
Yep, I'm good.
Here is another item of discussion that I really want you guys to remember since you brought this one up, Byron. I really had it in my mind too, is you really have to make a note in here of the differences between the two. Because sometimes this is actually what tricks my students in the first exam in the midterm. They remember the laws. One of them is the sum of the inverses inverted, and the other one is the sum of the direct values, okay? So you need to know which one is which, number one. Number two also, and this is a typical problem that really, I mean, it's annoying so much when I see it, and I really hate it when I see it, when my students do that, when they forgot to invert the final value. They take the inverse and the inverse and the inverse and add up the inverses and tell me this is the answer for the capacitance, for example, or the resistor, for example. In this case, they add up the inverse of the resistor and the inverse of the resistor and the inverse of the resistor, and they say, okay, this is the resistor, and then they come up with some nonsense value for the currents, and everything else is wrong based on that thing because they forgot to invert the sum of the inverses. So this is actually the sum of the inverses. So at the end, when you add up all of these numbers, invert your answer to get the R equivalent. Same thing with this, guys. Once you sum up the inverses in here, when they are capacitors in series, in series, then don't forget to invert the inverses, the sum of the inverses, I should say. Don't forget, after you sum up these things, this is not actually C equivalent. This is 1 over C equivalent. That's why this is item 2 of the discussion. I usually make a big fuss over this one, and today I forgot because we got into the time constraint, and I know we went 6 minutes already over time. So I'm sorry for that. But I hope that you guys caught this thing in here too. Make sense?
Yes.
Yes, Professor.
Very-
Thank you.
Thank you, guys. So I'm going to stop the recording now. Stop sharing first and stop the recording.